Welcome back to Think Cosmos, where we ponder the universe's deepest secrets and wonders. Meanwhile, far from Earth, a spacecraft older than many of us just got a new lease on life. NASA's Voyager 1 probe, launched in 1977, is humanity's most distant explorer, drifting so far that its radio whispers need almost a full day to reach us. Picture a lonely craft surfing interstellar night. The sun now just another bright star behind it. After almost 48 years of travel, Voyager 1 has cleared the heliopause and is sampling particles born between the stars. It has endured cosmic rays, bitter cold, and the slow dimming of its nuclear heart, a plutonium power source that fades a little each year. Yet recently, the veteran traveler faced a crisis closer to home. Its attitude control thrusters were wearing out. These thrusters are tiny rockets that nudge the spacecraft so its high-gain antenna stays locked on Earth. If they fail, Voyager would slowly tumble. The antenna would miss our planet, and the mission would fall silent forever. Engineers had watched performance degrade for years. Propellant lines were clogging, valve springs aging in vacuum. Every maneuver required more pulses, more fuel, more power than the time before. Fortunately, Voyager carries a backup set called the Trajectory Correction Maneuver, or TCM, thrusters. They were last fired in 2004 to line up a gravity assist shot past Saturn and had been dormant ever since. Imagine asking an engine left in a freezing garage for 2 decades to roar back to life on the first turn. No one knew if hydrazine would still flow, or if seals would crack after 40 years of cryogenic chills. Complicating matters, only one giant deep space network dish in California can send commands strong enough to reach Voyager. That dish was slated for maintenance in May, missed the window, and the probe would drift uncorrected for months. So in March, the Jet Propulsion Lab crew planned a Hail Mary fix. Wake the sleeping thrusters before the dish went dark. Because Voyager is nearly 24 billion kilometers away. Each command needs about 21 hours to arrive, and the reply needs 21 hours to return. Picture pressing send, then waiting almost 2 days to know if you saved a national treasure or doomed it. The team prepared a cautious script. Power on backup heaters, warm the fuel lines, then command a short 10-millisecond puff. They modeled thermal stresses, calculated momentum changes, and prayed the fuel tanks wouldn't slush freeze mid-sequence. At last, the packet left Earth, riding a 70-meter dish's microwave beam, thinner than a laser pointer. Then came the excruciating wait. Engineers pacing hallways, refreshing telemetry plots that stayed stubbornly blank. Finally, a carrier tone popped onto their screens. Data trickled in, showing a tiny temperature bump inside the TCM module. Moments later, attitude sensors registered a precise nudge. Voyager had fired the backup thrusters cleanly. Coffee cups hit the ceiling, and a cheer echoed across mission control. Yet another miracle saved for Voyager, a veteran flight director said, wiping away tears he blamed on dry room air. These thrusters, assumed dead, now promise to keep the antenna steady for perhaps 3 more years. That may sound short, but each extra orbit the probe completes around the Milky Way's center is a scientific windfall. Voyager's instruments still measure plasma density, map interstellar magnetic fields, and catch cosmic ray bursts from distant supernovae. Every fresh data point fine-tunes our models of how the sun's influence fades into true galactic space. Engineers also use the opportunity to tweak software written in 1970s assembly language, squeezing a few more watts from power reserves. They powered down an unneeded heater and rerouted that energy to the cosmic ray detector, granting it an extended lease of its own. This is duct tape spacecraft engineering, MacGyvering with bits instead of bolts across 24 light hours of emptiness. The rescue underscores how resilient good hardware can be when paired with relentless human ingenuity. Voyager's main computer holds just 68 kilobytes of memory, less than a single selfie on your phone, yet it still runs flawlessly. Its radio transmitter is a 22-watt bulb. A refrigerator light is brighter, but careful pointing and massive dishes make the link work. Each time we find a workaround, we learn lessons for future interstellar probes that may leave our network coverage for decades. Designers of nuclear sailcraft or laser-pushed starships study Voyager's power budget tricks to plan century-long missions. They're already debating modular thruster pods that can be woken after 100 years, inspired by this very maneuver. The fix also matters emotionally. Voyager carries the golden record, our cultural mixtape for any cosmic neighbors. Keeping that message broadcasting a little longer feels like holding a candle against the vast dark, refusing to let it snuff out. Some dream that a future starship might rendezvous with Voyager, retrieve the old probe, and display it in a museum orbiting Alpha Centauri. To pull that off, we'll need propulsion breakthroughs, maybe fusion drives or antimatter catalysis, technologies still on drawing boards. Ironically, data Voyager sends back now may help those designs. Its plasma readings refine models of interstellar drag on high-speed sails. The revival also highlights the deep space network's importance. Those 70-meter antennas are the umbilical cords of exploration. As traffic grows, from Artemis moonships to Mars sample return craft, expanding the network becomes urgent. Engineers propose laser comm relays and autonomous error correction. So far-flung probes can phone home with less babysitting. Voyager Save proves that even 1970s tech can adapt. Imagine what smart, self-healing systems aboard future probes could do. One concept is AI thruster management that learns wear patterns and switches valves long before clogging begins. Another is 3D printed propellant paths seeded with graphene heaters that clear ice on demand. These ideas trace their lineage to Voyager's patched-up thrusters and the humans who refuse to surrender. Every additional year Voyager survives also buys time for its twin, Voyager 2, which might tap similar tricks when its thrusters falter. Together, the pair provide stereo measurements of the galactic environment, something no other mission can match for decades. Astronomers use their readings to calibrate heliosphere models that inform space weather forecasts vital to future crews heading to Mars. Thus, a tiny hiss of hydrazine in deep space ripples into practical benefits back home. The saga reminds us that exploration is as much perseverance as rocket fuel. If we can nurse a 50-year-old probe across 24 billion kilometers, we can maintain solar power farms on the moon or habitats under Europa's ice. Voyager's heartbeat tells future colonists that long missions are survivable with careful stewardship. Someday teachers may show class schematics of the backup thruster firing and say, "This is how you troubleshoot when your lab is the galaxy." For now, Voyager 1 sails on, an honorary ambassador whispering tales from the interstellar sea. Each transmission is a postcard from humanity's farthest frontier, stamped with ingenuity and signed by the people who keep listening. And somewhere in that faint carrier wave is a lesson. With patience, creativity, and a dash of courage, no distance is too great, and no machine is ever truly beyond hope.